Yeah, so hi all. Uh, Very good evening and welcome back to the seventh week of the live sessions for artificial intelligence search methods for problem solving. Um, so first of all, can you hear me properly and is my screen visible? Okay, great. Thanks for the confirmation. Um, Yeah, so this week we'll be discussing some questions from week 7 content. So, till this while, till week 6, we had been discussing problems related to finding optimal paths or different search methods, right? So, this week we'll be getting into a bit of planning and strategies, and we'll be seeing methods like alpha, beta, and SSS star. And before that, we'll be looking at some game trees and some questions based on these topics basically, and hopefully they'll help you solve your assignments in a better way. So, yeah, maybe we'll wait for 2 minutes for people to join in and then we'll start with the questions. All right, so now let's get started. I think it's about time. So, okay, so we have broken down the questions into different segments. So that is just for demarcation of the different topics that we'll be covering. But yeah, let's move on to the first question. The first question is related to the alpha beta algorithm itself, which you might have seen or encountered in your lecture videos if you have seen them. And so this question basically gives the pseudocode for the alpha beta algorithm, and it asks us to identify which line numbers are the ones where the alpha cutoff and the beta cutoff are occurring. Okay, so you see the line numbers on the left hand side of the pseudocode. You basically have to identify the point where the alpha cutoff is happening and the point where the beta cutoff is happening. Okay, so you already have a couple of answers and that's great. So 6 and 11 is the suggestion. Okay, so which one of these is the alpha cutoff and which one of these is the beta cutoff? Let's take line 6 first. So in line 6, do you think it's a beta cutoff and or is it an alpha cutoff? Okay, we have one answer that says 6 is a beta cutoff and 11 is a alpha cutoff. What about the others? Okay, there's another answer that uh, says the same thing. Okay, so we have a couple of answers. Let's quickly look at the correct answer. So the correct answer is that in line 6 we have a beta cutoff, and in line 11 we have an alpha cutoff. So if you notice over here, so one important point to note is that whenever the node is a max node, okay, and this condition for cutoff, so the condition for cutoff is same when the alpha value is greater than or equal to the beta value. Whenever this condition is met, a cutoff will happen, but whether that will be a beta cutoff or an alpha cutoff, that will depend on the node that you are, type of node that you are going to inspect. Okay, so if n is a max node, which we usually denote by a square, and it has some min nodes as its children, and when that happens and some cutoff criteria is met and something is cut off, that will be a beta cutoff. Whereas when n is a min node, which is usually denoted by a circle, and it has some max children, and then some cutoff occurs, that will be an alpha cutoff. Okay, so that is one quick uh, insight about the alpha beta algorithm. We'll see more of it um, when we go through the one elaborate example on the implementation of the alpha beta algorithm. So what is cutoff? Good question. So cutoff is basically you're trying to prune away some parts of your game tree, and that is so that you basically you're trying to get rid of the strategies, game strategies that won't be helpful for you in the long run in achieving the objective of whatever game you are taking part in. So this is one of the methods to prune such strategies and get rid of them. Okay, so yeah, that was a fairly straightforward question. Um, let's move on to the next question, which is about game trees. Okay, so we have been given four two-player game trees. Okay, so we have four options A, B, C, and D, and these four two-player game trees are shown with some edges as highlighted in bold. Okay, so you notice some of these edges are darker than the other ones. We have to decide or select which of these depict the game strategy for the root node, which is a max node. Okay, so I'll zoom in a bit maybe for you to see the diagram more clearly. So we are given four game trees. Each of them has a max node as the root node, and we have to decide which of these depict a valid or a correct game strategy for this root node, which is a max node. Okay, so I'll let you go through the question and the game trees so that you can share your answers in the chat box. So a game strategy is basically so you could say take something like some game like, let's say, chess. Okay, so there one player starts with a move. Okay, depending on that move, the other player follows up with another move. Okay, so okay, discard chess, take something very simple like a tic-tac-toe. Okay, so uh, one player starts with filling in one of the boxes with either a cross or a circle, right? And then another player, depending on what the first player did, he or she selects another option. Okay, and both these players are trying to maximize their value, which is basically to win the game, right? So a game strategy is basically a set of these consecutive moves that the players would make, and that forms different subtrees of this whole big game tree. Okay, so I hope that answers your question to some extent, but if you want a clearer explanation, I would recommend that you uh, visit the lecture uh, videos that Professor Kemani has uploaded, and there you'll find a much better and a much crisp explanation. Um, okay, so we already have a couple of answers. So there was one request for repeating the question. So the question is just mentioned in the slide over here. Basically, we are given four game trees and we have to select which of these depicts a game strategy for the root node, which is a max node. Okay, so the keyword over here is that the root node is a max node. Okay, let's have a look at the answer now. So if you look at the first game tree A, so here what we are doing is we are selecting one of the children of the root node, okay, which is a max node. Fine, fine up to this point. Now, when we are at this particular min node, which is a child of this root node, this is the root node, okay, it is also selecting only one of these children, okay. But if you remember from the lecture recordings, that is not how these game strategies or these game trees are built, right? So when you have to select the children of a max node, you select one of the children of the max node. But when you select a child of a min node, you have to select all options, okay. So here, this since this is not selecting this particular edge, this is a wrong option, okay. So this can't be a game strategy for the root node. Now let's look at game tree B. Here we are selecting one child of the max node, which is fine. We are selecting both children of the min node, which is again fine. We are selecting one child of this max node and one child of this max node, which is also fine. And then we are selecting both children of the min nodes respectively. Okay, so this particular strategy can be a game strategy for the root node. This makes sense. Now let's look at game tree C. Here also it makes sense because we are following all the conditions that we were told in the lecture videos. For each max node, we are selecting one of its children. For each min node, we are selecting all of its children. Okay, so game tree C is also valid. It's a valid game strategy for the root node. In game tree D, we see that this is selecting all possible children of the root node. So here itself, we can say that this is a wrong option. Okay, so the correct answer in this case would be game tree B and C are depicting a game strategy for the root node, which is a max node. In case of a min strategy, you will follow whatever conditions we just checked for, as in you look whether all children of min node have been selected or not. But usually when we build game trees, we select a max node as the root node. Okay, so having a min node as a root node is rare, and it's not really prevalent. I hope that answers your question. Okay, so yeah, thumbs up to everyone who attempted this question and also answered it correctly or incorrectly. It doesn't matter, as long as you get the understanding. Okay, so let's move on to the third question. So questions 3 to 5 will be covering a slightly different topic from what we saw in questions 1 and 2. Not completely unrelated, but slightly different. Okay, so this is question 3. So this figure shows a game tree uh, with evaluations. W represents a win. Okay, so you'll see that some of these boxes are filled in with W. That basically means that it's a win. L represents a loss and D represents a draw from Max's perspective. Okay, again notice that the root node is a max node, and in this game tree, the labels P, Q, R, and S indicate the strategies or moves at the level of root. Okay, so basically from the root we have 4 possible directions we can proceed in, uh, which is P, Q, R, S. Okay, and basically this is a half filled game tree, and what we have to do is we have to fill up the whole game tree to decide what will be the outcome, whether it will be a win or a loss or a draw from the max's perspective when both the players play perfectly. Okay, so one important distinction that I want to make here is that please don't confuse this game tree with the search trees that we have been seeing till now. Okay, so in search trees it's a different concept. Here the subtrees represents strategies. Okay, not it's not basically the search tree and this game tree are not equivalent. That's just a point that I wanted to make. Okay, so yeah, I'll give you a couple of minutes to try to solve this question, and then we'll have a discussion on this. In the meanwhile, there was a question on if whether option D is the answer for min. I suppose you're asking this in context of the previous question, Pranav. Um, could be, but since even in the option D that we saw in the previous question, the root node was a max node. We can't really say that it's a correct option in for a particular question. You can try replacing the root, the max node and the min nodes, and you can see whether the conditions are met. And yeah, if that is satisfied, then that can be a strategy for a min from the perspective of min. But yeah, getting back to this question, the third question. Yeah, I'll give you a couple of minutes and then we can discuss. In the meantime, if you have found the solution, you are welcome to write it in the chat box. Okay, so you have many of you have already given the answers, so that's great. Let's have a discussion on which of these is the correct answer. And yes, Ram, don't worry. I've already shared the presentation slides and as well some supplementary material for you to answer the questions better for the live session questions, not the assignment question. So yeah, the video I'll try to get it uploaded by tomorrow. So yeah, let's solve this particular question. So the way you can see this is you can see it as, you can assign a value of +1 to W, you can assign a value of -1 to loss, and you can assign a value of 0 to D. Okay, and what a max node will try to do is it will try to select the maximum value from all its children. Okay, so if it had, let's say, a 1 over here and a 0 over here and a -1 over here, it would try to select some the maximum possible value, which is 1. And if it had been a min node, it would try to select the minimum possible value. Okay, so based on that, let's just try to fill everything up. So this is a min node, and the first one, this one, and it only has 3 options to choose from, all of which are wins. So this will have a win over here. Now this max node above it, this one has options draw, win and loss. So it will choose the win again because it will try to maximize, right? And now let's fill up this part. So this has options W, L and W, and it's a min node, so it will choose L. Okay, and this max node now has 2 options which are both losses, so it will again go for L. And this min node has to choose from a win, a draw and a loss, and it being a min node will choose loss. Okay, now let's consider the strategy Q. So this is a min node which has options draw and win, so it will go for a draw, which seems to be the lowest option among draw and win, because this is 0 and this is +1, right? This max node will go for a win, this one will go for a loss, this one will go for a loss, and this one will go for a draw. Okay, now this min node has to choose from a win and a draw, and the lowest looking option over here is a draw, so it will choose a draw. Okay, now similarly for strategy R, this min node will have a draw over here, it will have a win over here, this will have a W, this will have a loss, and this will have a loss. Okay, is everything clear up to this point? I think I'm making some mistakes, so let me just quickly check it. What is the mistake that I'm making? Right, this is a mistake. It won't select a win, it won't select a loss, it will select a win. Yeah, correctly pointed out. So this will be a W, not a loss. Sorry for that. This is a max node, so it will select a win, and this will have a win. Yeah, yeah. Okay, let's do similarly for the strategy S. This will have a draw, this will have a win, this will have a win again, this will have a loss, this will have a win, and this will have a win again, but this will have a draw. Okay, so out of loss, draw, win and draw, this root node will select a win, so the final value would be a win, and that is our answer. So let's check the solution now. So the outcome of the game when both players play perfectly would be a win, as we just saw. Okay, any confusion about the game tree, how we filled it up? Because later on we are going to get into a slightly more advanced version of this game tree. So it's good if this is clarified. That's great. Okay, now let's move on to the next question then. which is also based on the same context, same game tree. But here we are asked which of the moves P, Q, R, or S are the best moves for max. So, um, Rocky, that is not always true. So the question is, when both players play perfectly, wouldn't it become a draw? That is not always true. That actually depends on the type of game you are playing. Okay, so it is said that in a game like chess, when both players play perfectly, it will end in a draw. But that is also largely because chess as a game has not been solved yet. Um, there are games which are very simple, and we know that if the starting player begins with a certain strategy, and then he or she is destined to win. Okay, then those kind of games are called solved games. So no matter how perfectly both the players play. Okay, so it's not always true that when both players play perfectly, it will end up in a draw. Um, okay, so yeah, that's right. So Q is leading to a draw. So here is the game tree that we filled in. So this root node, which is a max node, this has uh, four strategies that it could choose from. Okay, the P strategy will lead to a loss. The Q strategy will lead to a draw. The R strategy though will lead to a win. Okay, and the S strategy will again lead to a draw. So the best strategy for this uh, max node or the root node would be the R strategy. Whereas strategies Q and S would lead to a draw. Okay, and that is what exactly is asked by this question and the next question actually. So which of the moves PQRS are best moves for max? It would be R, because R would lead to a win. Okay, and a follow-up question is, which of these moves lead to a draw if both play perfectly after the first move? That would be Q and S. Both Q and S would lead to a draw. Okay, yeah, sure. I'll quickly repeat it once more. So basically what we are saying is, for this max node, uh, yeah, there are four strategies that it could follow. One is strategy P, strategy Q, strategy R, and strategy S. And we see that out of all of these, R is the one that will lead to a winning move. Okay, this W, that is the final answer or the final value of the game that this root node is attaining, is coming from the R strategy, right? So this R strategy will lead to a win for the root node. Whereas strategies Q and S would lead to a draw, because these are having a draw option. Okay, and if it had followed this P strategy, it would have led to a loss. Okay, so that is basically what is asked in questions 4 and 5. It is asked which of the strategies P, Q, R, and S would lead to a win, and that would be strategy R, and which of these would lead to draw would be strategies Q and S. Okay, if more than one wins are present, then any of those strategies would be good enough, right? As long as the player is winning, any of the winning strategies would work. Okay, so any doubts till now? Okay, that's great. So let's now move ahead to the next few questions, question 6 onwards. So from here on, we'll use a slightly more nuanced version of game tree. So earlier we were dealing with just wins and losses and draws. So here we are actually going to have numbers instead of just wins and losses and draws. Okay. Okay, so before moving on to the questions, let's just go through a short description of the game tree. So the figure over here shows a 4-ply game tree, okay, with evaluation function values at the horizon. So the horizon is basically the line at the, or the sequence of nodes at the bottom, okay, the list of nodes at the bottom with the numbers filled in, that is the horizon. Okay, before that, does anyone remember what is meant by a 4-ply game tree? Yeah, exactly. That's right, Pranav. We can, so when in a game tree, we are looking at the next four possible moves. We call that a 4-ply game tree. That is, yeah, basically looking 4 moves ahead. So yeah, that's great. Thanks for the answer. And let's complete the description. So the nodes in the horizon carry reference numbers, which is the index given at the bottom of the horizon, which is 1, 2, 3, 4, so and so forth up to 24. And we will be using these reference number when we want to enter a list of nodes. Also, when we want to address each of these nodes, it will be helpful to have these reference numbers in mind. And where necessary, we will assume a top down and left to right node order. Okay, and we will use this particular game tree to answer the coming questions. Okay, now on to the question itself. So this question asks us to use the min-max strategy, and using that min-max strategy, we have to fill up the whole game tree and list the nodes uh, using the reference numbers that are a part of the best strategy, and also the min-max value that the game will be attaining. Okay, so yeah, I'll again give you a couple of minutes to try to solve it, and then we'll have a discussion about the solution. So yeah, I'll just quickly say 4-ply basically means that a person or a player is looking 4 move aheads into the game, and he or she is planning their uh, game strategy by looking 4 moves ahead. Okay, so yeah, let's take a couple of minutes and then we shall discuss the solution. Okay, it's great to see that so many of you have answered the question and answered it correctly. So that's great. Let's have a quick look at the solution. Okay, so we have to follow the min-max strategy. So let's have a look. Let's start from the left-hand side. So this min node has to choose from 64 and 80. So it'll choose 64. Let me write that down. And this has to choose from 69 and 68. So it'll go for 68. And this in turn will choose 68. Okay. Now this one will choose 72. This one will choose 16. And this one will choose 72. and this one will choose 68. Okay, now one subtree is filled up. Let's fill up the other subtree. So this one will have 17, this one will have 13, because it's choosing the minimum of the two options that it has. Now this one will choose 17 because it will choose the maximum of the options it has. This one will choose 58, this one will choose 57, and this one will choose 58, this one will choose 17. Okay, now to the last subtree, this one will choose 62, this one will choose 31, this one will choose 62, this one will choose 11, this one will choose 36, 36 again, and here also 36. So the final root node value would be the maximum of 68, 17, and 36, which is 68. Okay, so as many of you say, 68 would be the min max value. Okay, so before going further into the solution, I'll just quickly address two queries in the chat box. So what does best strategy mean in SSS star? We'll discuss that when we discuss the SSS star algorithm. We will cover that, which is towards the last few questions. And when we cover that, we'll where hopefully the example that we cover will help you answer your query. And what does it mean? List the best nodes. List the nodes in best strategy. So basically, the best strategy that you found over here in this game tree with a value of 68, you have to decide which are the nodes at the horizon from which that 68 value is coming up. Okay. So based on this game tree, what do you think would be those nodes at the horizons? You can write down the reference number of those. Okay, 4 maybe. Is 4 the only horizon node that is contributing to the best strategy? Okay, will 1, 2 really be part of it? Okay, let's have a look. So basically this 68 is coming from this min node. Okay, and this min node is getting its value by comparing this max node and this max node. Okay, now let's consider this max node first. This max node with the value 68 is getting its value from this min node, which is 68, which in turn is getting its value 68 from these two nodes. Okay, so 3 and 4 are definitely part of the best strategy. Now let's have a look at this 72 node. Okay, so the 72 max node is getting its value from this min node. Okay, and this min node in turn is getting its value 72 from these two max nodes. Okay, so 5 and 6 are also part of the best strategy. So the answer would be all these 4, 3, 4, 5, and 6. These are part of the best strategy. Okay, and if you remember, when we choose a child of the max node, we choose one of its child. When we choose a child of a min node, we choose all of its children. Okay, so that's how you construct the strategy. And the best strategy in this case corresponds to this particular highlighted. Uh, okay, let me just highlight that subtree. So this is the one, this one, this one, and then this is the best strategy. And the nodes that are contributing to this are 3, 4, 5, and 6. Okay, does that provide some clarity? Okay, great. Let's have a look at the solution quickly. So yeah, as we saw, the min max value of the game is 68 and the nodes in the best strategy are 3, 4, 5, and 6. Uh, sure, I can use the red color from the next question. Will incorporate that. Okay, let's look at the next question then. So the next question now asks us to simulate the alpha beta algorithm on the same game tree. Okay, so the same game tree, we simulated the min max method on this game tree in the previous question. And now we are asked to simulate the alpha beta algorithm on game tree, the same alpha beta algorithm whose pseudocode we saw in the first question. And then we have to report what is the number of alpha cuts and what is the number of beta cuts. And one thing to note is that when we make either an alpha cut or a beta cut, it is possible that that single cut would remove a bunch of edges at once. What it means is that a single cut may result in pruning of not just an edge but a small subtree itself. Okay, so we can keep that in mind when we solve it using the alpha beta method. And yeah, so I'll give you again a few more minutes because the alpha beta method is a bit more involved. So I'll give you some few minutes to try to solve it on your own first and then we'll have a discussion. Okay, you can write down your potential solutions when you arrive at one in the chat box if you get that in the meantime. Okay, so yeah, any potential or even partial solutions that you might have obtained till now? Have you encountered any alpha cut or any beta cut in your partial solution till now? Okay, no worries. Let's try to do a step-by-step solution, and let's have a look at that. Okay, so I'll use the same diagram. Okay, I'll remove the solution for the min-max strategy, and then we'll begin with the alpha beta algorithm. Okay, okay, so yeah, so what we will do is we will initialize. So each of these nodes over here will have a copy of the values of alpha and beta. Okay, and these alpha beta values will we will initialize them to a certain value, and these will keep getting updated as we move through the solution, move through the algorithm. Okay, um, so you could think of alpha as a lower bound and beta as an upper bound. Okay, so what is something that could be a lower bound? It could be minus infinity. Okay, so nothing can be lower than minus infinity. So let's initialize our alpha as minus infinity and beta as plus infinity. Okay, so this is our alpha, this is our beta. Okay, so this is looking a bit like a T, it's just a plus. Okay, so this is how we'll initialize our alpha and beta, and we will pass it on to each of the children. Okay, so let's first pass it on along this line. Okay, so I'm not writing alpha beta again and again, so just note that alpha is the top one and beta is the bottom one. Okay, so again it will be passed minus alpha and plus alpha, again minus alpha and plus alpha, again minus alpha and plus alpha, until it reaches this horizon node, which is a leaf node or the node at the bottom. Okay, now this will return a value of 64. Okay, and 64 is less than this value, that beta value of the beta for this particular min node. Okay, for this min node the value of beta was infinity, plus infinity, and the 64 is lesser than that. So what it's going to do is it will update the value of beta. Okay, so the value of beta will now become 64. Um, okay, I'm not sure whether I said it correctly. Um, Basically, what will happen is that I think I might have confused it to be a greater than or lesser than. Basically, 64 is lesser than alpha, so it'll update beta value. Okay, if I had spoken it the other way around, please uh, ignore that. Okay, so is it clear up till this point? Okay, just give me a moment. Okay. Okay, yeah, sure. Sorry for that. Yeah, I'll repeat from the beginning again. So basically what we are doing is we are initializing our values of alpha and beta to be minus infinity and plus infinity respectively. And we are starting with a top down and left to right approach. Okay, as the description had mentioned. Okay, so we are going down this way. Okay, so this max node had a value of minus infinity for alpha and plus infinity for beta, and this it passes down to its first min child, and this in turn passes it to the first max child. This in turn passes it to the uh, let me make this infinity again. Yeah, it passes it to its first min child, and this one in turn looks at its first max child which has a value of 64. Okay, so this horizon node will be returning a value of 64, and since that is lesser than this plus infinity value for beta, this beta value will be updated to 64. Okay, let me just remove these tick marks. Now, once these beta value has been updated, this set of beta value will now be sent to, not exactly sent, but this set of beta values will alpha and beta values will be used to uh, uh, check the conditions when we go to the second horizon node, which is this 80 node over here. Okay, so here we see that 80 is greater than 64. Okay, so we don't need to update beta over here. Okay, so we don't need to update beta, and we'll fill in the value of this min node and we'll call it 64. Okay, now when this has been filled, this min node has been filled with value 64. This will now pass on this information to its parent, which is this max node. Okay, and since this is a max node, and since 64 is greater than minus infinity, the alpha value will now be updated to 64 for this max node. Okay, so this max node now has alpha value 64 and beta value plus infinity. Are you with me up till this point? Okay, that's great. Um, okay, now what this will do, now it will look at the next min child that it had, and it will look at it with the updated values of alpha and beta, which is 64 and infinity. Okay, now this will be compared against this 69 node. Okay, and this is lesser than infinity, so this will now get changed to, the beta value will get updated to 69. Okay, and now again this updated value of alpha and beta, which is 64 and 69, that will now be sent to or used to compare against this 68 horizon node. Okay, and again this is lesser than the beta value, which is 69, so the beta value will again get updated. Okay, and the beta value will now become 68. Okay, and now we have covered both the 69 and 68 node, and we have got a beta value of 68. So we will fill in this min node with a value of 68. Okay, any confusion up till this point? Okay, let me repeat it once more. Okay, it's great to see this thumbs up, so thank you for that. Um, yeah, so 64 is the lesser value, but 64 is the alpha value, not the beta value. Okay, and this is the min node that we are considering. So the min node will be filled up with the beta value unless there is an alpha cutoff. And here the alpha cutoff condition is not yet met. Uh, okay, so basically what we did was when the 64 infinity, we passed it down and along this direction. Okay, this had value 64 and plus infinity. When this was used to compare against the 69 node, 69 is lesser than plus infinity, so beta value was updated to 69. Okay, and this updated alpha beta value of 64 and 69 was then used to compare against the 68 node, which returned a value of 68, which is again lesser than the current beta value, which was 69. So the beta value was again updated to 68. Now that we have covered both 69 and 68 nodes and there are no more children of this min node left, we will assign the beta value to this min node, which is 68. And once it has been assigned that, it will now pass on this information to its parent just like the previous case. Okay, so it will again pass on this information, and now what do you think will happen? Will the alpha value get updated or not? Yeah, it will do so because 68 is greater than 64. Okay, so this alpha value will now change to 68. Okay, and again, so now both the children of this max node, this particular max node, they have now been assigned a value. Okay, and the alpha beta value for this particular max node has been updated accordingly. So we can say we can also now fill in the value for this max node and we can assign it a value of 68, which is the alpha value. Okay, so this beta value for this max node is remaining plus infinity only, right? We didn't change the beta value. So remember what I said at the beginning, each node will have its own copy of alpha and beta values, and it will keep changing as and when we go through the algorithm or move through the steps of the algorithm. Okay, so when the changes to the beta values from infinity to 69 to 68 that were happening in the lower subtree, that were local to the copies of alpha and beta that were present in that subtree. Okay, now that this max has been also assigned a number, this will again pass on this information to its parent, which is a min node. And what do you think will happen? Will the alpha value change or the beta value change? Correct, beta value will change and its value will change from plus infinity to 68. Okay, so this will now become 68. Okay, and now this will pass on this information to its next uh, child max node, which is this one. Okay, and it will also pass on this same value that it had is minus infinity and 68, and this again will pass along the same values minus infinity and 68. Now this will then compare it against this 90 node. Okay, so this 90 horizon node will return a value of 90, which is greater than 68. So what do you think? Will the beta value change or not? That's correct. It won't change. So this will be okay. So the beta value did not change. Now we will look at the 72 horizon node. Again, 72 is greater than 68. So again, the beta value will not get updated. The beta value will remain 68 and we will fill in the min node with the beta value, which is 68. Okay. And now, is it clear up till this point? Okay, that's great. So Okay, now that we have filled in 68 for this min node, this will pass on this information to its parent, and this parent is a max node with an alpha value of minus infinity. So what do you think will happen now to the alpha value of this max node? It will become 68, right? It's the 68 is greater than minus infinity, so the alpha value will get updated from minus infinity to 68 for this max node. Now do you think that a certain condition has been met? Remember the condition for cutoffs. It was when alpha is greater than or equal to beta. So is that condition being met now? That's correct. So which means that now it's time for a cutoff, right? So what kind of cutoff will it be? Remember from the first question when we solved the pseudocode, when you saw the pseudocode, we said that if the node is a max node and the cutoff condition is met, then it will be a beta cutoff. That's right. So now it will have a beta cutoff, and let me just show the cutoff with a different color so that it's not confusing. We will cut off this particular edge, and this in turn will also cause the severing of these two edges. Okay, so basically this whole small subtree that we had, okay, the one that I am covering with this yellow uh, boundary, this whole thing will be cut off. Okay, this is a beta cutoff. So this cutoff happened, and now this max node will be filled in with the value 68. Okay, so was the cutoff clear? Any confusions about the cutoff till now? Okay, so basically that yellow region is the region that we have cut off because of the beta cut that we just saw. Okay, so you saw that for that max node, the alpha and beta values were same, right? And that is one of the conditions for cutoff. Alpha has to be greater than or equal to beta. And here we see that alpha is equal to beta, which is 68. So a cutoff happens, and that cutoff cuts off the immediate next edge that is there. And that cutting off that particular edge, basically this particular edge, results in a severing of this whole little subtree that was there. Okay, so this whole subtree is cut off, and that is a beta cutoff. Okay, that's great if there is no confusion till this point. Now what will happen? This max node will also send this information to its parent, which is a min node. Okay, and here the beta value was already 68, and this is also passing on a value of 68, so the beta will remain unchanged. Okay, and since both the children of this min node have also been solved, this will be assigned a value of 68. Okay, and once this has been assigned a value of 68, this in turn will pass on this information to its parent, which is a max node, and here the alpha value will now get updated to 68. Okay, are you with me up till this point? Okay, so yeah, alpha value will be updated on max node and beta values will be updated on min nodes. So I am purposefully moving very slow because I feel that alpha beta method is a bit confusing. So Please bear with me if it's the solution is looking a bit slow, but hopefully by the end of it, it'll all be more clear. Okay, so if there's no confusion up till this point, now let's continue with the rest of the solution. No, the root node beta will not be 68 because beta will remain plus infinity. The root node is a max node, right? So we'll update the alpha value, not the beta value. Okay. All right. So now that we have this updated set of alpha and beta values, this will be passed along to its next child, which is this min node. So it will get 68 and infinity. This in turn will pass it over here, which will also get 68 and infinity. Now this will also pass it over here, which will get 68 and infinity. And this will now compare it against this horizon node, which is returning a value of 17. Okay. So when this returns a value of 17, what do you think? The beta will get updated or not? Yes, it will get updated because 17 is lesser than infinity, right? So the beta value will get updated and change to 17. But now that the beta value has been updated, do you think the cutoff criteria is met once again? Yes. So once again, alpha. So this time, so earlier we saw that the cutoff was for when alpha was equal to beta. This time we see that alpha is greater than beta. Okay, so 68 is greater than 17, and we see that alpha is greater than beta. So the cutoff criteria has been met once again. And so there will be a cutoff of the next immediate node, which is this 84 node. Okay, so let me mark it with a different color to. Okay, so first of all, what kind of cutoff will this be? Will this be an alpha cutoff or a beta cutoff? That's right. It will be an alpha cutoff because it's a min node where this condition, the cutoff condition has been met or it has occurred. Okay, so this edge will be cut off. Okay, which basically means that this little subtree is going to be cut off. Okay, this is an alpha cutoff. Okay, and once we have done that cutoff, now it will be assigned a value of 68. Okay, remember now we are assigning the alpha value to this min node instead of the beta value because a cutoff happened. Okay, otherwise in usual conditions, the min node is assigned whatever the beta value was there. Only in case of a cutoff, a beta value, a min node is assigned the alpha value and max node is assigned a beta value. You can also quickly check the pseudocode that we saw, right? So if n is a max node and the cutoff criteria is met, then we assign it a beta value. Otherwise, it's an alpha value. And if it's a bin node and the cutoff criteria is met, then we assign an alpha value. Otherwise, we assign the beta value. Okay, now let's move ahead. Okay, so now that we have now that it has been assigned this value 60, this will now pass on this information to its max node, its parent node, which is the max node, and it already has an alpha value of 68, right? So no changes in the alpha value will happen because 68 will remain 68, and it will now pass on this set of values 68 and infinity to this min node. Okay, and this min node will now use this to compare it against this 13 horizon node. Okay, now what do you think will happen when we compare it with the 13 horizon node? That's right, beta update will happen. It will be updated to 13. Okay, so this beta will be changed from infinity to 13. Okay, and once again we see that alpha is now greater than the beta, right? So again one more alpha cutoff will happen, and this particular subtree will be pruned. Okay, and again this will also be assigned a value of 68. Okay, this will also pass it on to its parent, which already has an alpha value of 68, so alpha value will remain same, and this will also get assigned a value of 68. Okay, yeah. Now that this max node has been assigned a value of 68, this will now pass on this information to its parent, which is a min node. Okay, now that this is a min node, do you think the beta value will get updated or not? Are you sure? Remember, it's a min node, so the beta value will get updated, right? No, no, no. Both are not infinity. Um, so this min node, this had a value of alpha as 68 and a value of beta is plus infinity. And when this particular max node, when this one is passing on the information of value of 68, returning a value of 68 to its parent node, which is a min node, the beta will get updated, right? The beta will get changed from plus infinity to 68. Exactly. Infinity gets updated to 68. And now, sorry about that. Once again, the cutoff criteria has been met. Both alpha and beta have the same value and they are equal. So again, a cutoff will happen. Exactly. That is right. Again, a cutoff will happen and this will also be an alpha cutoff. Okay, because we are currently at a min node. Okay, so this edge will cut off. Okay, and because of this whole subtree that is there, that whole subtree will be pruned off. Okay, so let's mark it. This whole subtree will be pruned off. Again an alpha cutoff. Okay, and this will again be assigned a value of 68. And once this has been assigned a value of 68, it will then pass on this information to its parent, which is a max node, which already has an alpha value of 68. So nothing change will happen in the alpha or beta value of this particular max node at the root. Okay, so it will continue to have this value of 68 and infinity. Okay, so now it will then pass it along to the next min child that it has, which would be 68 and infinity. These are the values of alpha and beta. Again, this will be passed on 68 and infinity. Again, 68 and infinity. Okay. And again, a similar situation will happen. Okay. So this 62 horizon node will return a value of 62, which is lesser than this plus infinity. So the beta value will again get updated to 62. And as a result, again we see that alpha is greater than beta. So again another alpha cutoff will happen, which will prune off this part of this small subtree, just like the previous case we saw. Okay, so this will get pruned off, and this will also have a value of 68. Okay, and this will now pass it to its parent, which already has an alpha value of 68. So no change in the this alpha value will happen. It will remain 68, and it will then pass on the 68 and infinity to the next child, which will again compare it with this 31 horizon node, and the beta value will again change from plus infinity to 31. Okay, and once again the same situation happens. Alpha is greater than beta, so again another pruning will happen, which will prune off this particular subtree. Quite similar to what we just saw in this particular this second strategy that we were looking at a couple of minutes ago. Okay, so this will also get assigned a value of 68. This will then pass on this information to its parent, which already has an alpha value of 68. So this will also get assigned 68, and this in turn will pass on this information to its parent, which is a min node. So the beta value will again get updated. Okay, and this will change from plus infinity to 68. And once again we see that the alpha and beta values are the same, so one more alpha cutoff will happen that will prune off this whole subtree. So you see how this alpha beta algorithm is helping you reduce the amount of effort you put into your strategies, right? It will help you prune off the unnecessary strategies. So again an alpha cutoff, this will get assigned a value of 68. This will then pass on this information to its parent, which is a max node with alpha value 68. So no change will happen there. And now that all of these children have been solved with value 68, this will also get assigned a value of 68. So now we have used the alpha beta algorithm to solve the whole game tree, to fill up the whole game tree, and we have encountered one beta cutoff and 6 alpha cutoffs, and we have obtained a final value of 68. Okay, so this is the final solution to the alpha beta algorithm. I will give you a couple of minutes to go through this and try to convince yourselves if you're not already convinced about the solution, and then we'll move ahead to the next few questions. And also for your reference, so this time along with the presentation slide, I've also updated something called a trace uh, information. Okay, so if you're having a look at the same folder where the lecture slides are used, not the lecture slides, the live session slides are usually uploaded. I've uploaded this particular PDF as well, which contains the traces. Okay, which basically means so this is a detailed step-by-step account of whatever just happened uh, in a more formal manner. Okay, so there is an SSR star solution also at the bottom, which we'll look at later on. But yeah, you can also refer to this one either now or later whenever you have time, um, at your own convenience. Okay. Okay. So I'll let you go through this for a few minutes, and then we'll move on to the next question. Yeah, Ankit, you had raised a hand. Did you have a question? Okay, seems like it was by mistake. No worries. Um, right. So yeah, so it won't be alongside the lecture material. It's been uploaded in the folder, the drive folder where usually the presentation slides for the live sessions are uploaded. Okay, so if you remember, this problem solving session led us to a link, right, which was a Google Sheet, and this had a presentation folder link. Okay, this drive folder. So if you just go to this drive folder, that will have this PDF available. Huh. So thanks for your message, Pranav. So yeah, so one thing that you could try to do is you could use the search functionality that is usually available in a different any PDF viewer. I think you use either in Linux or on Windows or on Mac, that will have some kind of a search functionality that you can use to search for keywords. And yeah, I do agree that sometimes the diagrams have are presented as images, so it's not really um, helpful if you want to search for something specific within a diagram. But yeah, I can pass along this information, but for now we have to do with what we have. Okay, so let's um so I think some of the lecture slides have their PDFs uploaded, right? Or most of them have their PDFs uploaded in the lecture material section on Swayam. So maybe you can check that out. um, I'm not sure if you're referring to the same thing or if I'm uh, efficiently answering your query, but uh, yeah, I hope that helps somewhat. uh, uh, yeah, so I see your message, Rocky. For alpha greater than equal to and beta less than equal to, I don't completely get your question. What do you mean by for alpha greater than equal to? Do you mean when will we update the alpha and beta values? If that is your question, okay, the condition for pruning will remain the same for irrespective of what node we are in. Okay, the condition for pruning is alpha greater than equal to beta. Okay, so whenever alpha greater than equal to beta, the pruning will happen. Whether it will be a whether it will be a alpha cutoff or a beta cutoff, that will depend on the kind of node that we are encountering. If I just go to the pseudo code, okay, so you see that the condition for pruning is same in both cases, alpha greater than equal to beta, alpha greater than equal to beta. Whether it will be an alpha cutoff or a beta cutoff depends on whether the node is a max node or a min node. All right. So now let's get back to our question slides. So yeah, so this question asked us to simulate the alpha beta algorithm on game tree 1, which is this game tree, and we had to report the number of alpha cuts and beta cuts. So we just saw the number of alpha cuts were 6 and the number of beta cuts were 1. Okay, so that is about it. Now, okay, now let's move on to a slightly different way. So this question now asks us, question 8 asks us, it's the same game tree, but this now asks us what is the total number of strategies in game tree 1? Okay, if we just consider the um, game tree itself, what is the total number of strategies? Remember that we looked at strategies a bit early on in the first two questions. Using that as a hint, what do you think will be the total number of strategies? I'll let you think about it for a while I'll just drink some water and come back. And yes, I will upload the Jamboard as well. Don't worry about it. Okay, so yeah, sorry about that. I'm back now. And yeah, so a couple of you have tried to come up with some answers, and all of those are good attempts. So let's now have a discussion to see how many strategies are actually there in this game tree. So Okay, looks like I have to continue using this slide. So let me just copy it to a different page so that you don't lose your alpha beta method. Okay, so huh. So let's consider one of the strategies. Okay, so remember, for a max node we'll select one of its children, right? So let's say we select this leftmost child, which is a min node. Now for a min node we'll select both children, this one and this one. Now again for this max node, now we are faced with an option. We can either choose this one, okay, and then we select both these, and from here we can select this one and then both these. This is one strategy, right? Do you agree with me? Okay, yeah. So some of you have already given the answer. That's great. Um, so this is one strategy. Another strategy could be, instead of choosing this one, we could have chosen this one. Okay, this could have been another strategy where these two would have been chosen then. This could be another strategy. Similarly, we could have chosen this one from this max node and either this one or this one from the other max node, right? So we see that for this particular option, this child node, okay, basically for this subtree we have four strategies. Okay, strategy 1, 2, 3 and 4. Similarly, for this subtree we would have four strategies, and for this subtree also we would have four strategies. The total number of strategies would be 12. Okay, so I hope that clears any confusion that might have existed. Great. So let's come back to the questions and let's check whether the number of strategies matches. So it does match. So there are total number of strategies of equal to 12. Okay, will it be number of terminal nodes by 2? I'll ask you to verify it by considering this game tree and some other game trees also that you could get a hold of. Okay, so try and see if that pattern always holds. That, yeah, so any map similar have same answer, so I'll let you figure that out. Okay, you can try drawing a game tree and try to figure out whether that happens again. Or if you have another game tree available in maybe some practice assignment or somewhere on the internet, you can try that also. Okay, so all right, now we come to the final algorithm, which is the SSS star algorithm. Okay, so here we are asked, so it's the same game tree once again, but we are using a different algorithm over here. We'll use the SSS star algorithm, and as you would recall, uh, for SSS star we need to start with a set of initial clusters, okay, which come from the horizon nodes. Okay, so there are two parts of this question. The first part asks us what is the initial number of clusters formed by SSS star, and what is the we have to list all the horizon nodes that are part of the initial clusters formed by SSS star. Okay, so a small intro of SSS star would take a lot of time, so it's not really possible to give a small intro. So we will get into an in-depth step-by-step solution to this SSS star method, and hopefully that will give you some intuition of what we are trying to do. Okay, and for a better explanation, you can check out the lecture videos. I would highly recommend that. Okay, so yeah, once again, I'll give you a couple of minutes to try to solve it on your own, and then uh, we'll quickly look at the solution. Okay, so a nice question here. So what exactly is a cluster? Okay, so there's one interesting difference in the strategies that we have been seeing till now and the kind of approach that SSS star adopts. So till now we have been seeing that we chose one child for max node and all children for min node. SSS star chooses the opposite. So for max node, it chooses all possible children, and for min node, it chooses one of its child. Okay, and that one of its child, we assume we fix it to be the leftmost child. Okay, so let me just switch on my video. Yeah. So basically, what that means is that it'll select all these. It'll select one for this, all for this, and one for this. Okay. Similarly, here it will select the leftmost child, all for this, and the leftmost child. Again for this, the leftmost child, all for this, and the leftmost child. So here you see we get a list of nodes, horizon nodes, which is 1, 3, 9, 11, 17 and 19. So these are basically our initial clusters, okay, or this initial set of uh, you could say strategies that we are going to uh, base the rest of our solution on. Okay, again, for a deeper explanation I would recommend you visit the lecture videos, but just on an intuitive level, uh, this is how you select the initial clusters. Okay, all right, so now let's get started with the solution of the SSS star method. So I'll erase this, and so you might have already noticed that I created another page on the Jamboard called the priority queue. So that is something that this SSS star method uses. Okay, so it will use a priority queue, and the priority will basically be decided by the value that is being returned. Okay, how about that? How that happens? Let's see that. Also, for the sake of clarity, let's just mention that um, for ease of for for it being easy for us to address the different nodes, let's name these different nodes. Okay, so let's call the root level as the level A. Okay, so this is the first node on level A, first and only node, so it will have name A1. Similarly, this will have name B1, B2 and B3. Okay, this will have C1, C2, C3, C4, C5, C6. This will have D1, D2, D3, D4, D5, D6, D7, D8, D9, D10, D11, D12, and each of these horizon nodes will have E. So it will have E1, E2, so on and so forth up till E24. Okay, I'm not writing the E for each of these horizon nodes. So that is a nomenclature that we are going to use, and that is how we are going to uh, put our elements into our priority queue. Okay, so what we do is we start with the root node, which is the A1 node. Okay, so let's see what we do. We enter A1 into our priority queue. So the way we enter it is we write the name of the node. Okay, we write the type of the node. So this is a max node. We will assign a status to the node, as in whether it has already been solved or not. So for now this node is live, it has not yet been solved, so we will say that it is live, and it has a bound of infinity and no value yet. Okay, so let's keep that blank. Okay, so this is our queue. So next what will happen is it will pop A1, and in place of A1 it will add all the children of A1, because remember A1 is a max node. A1 is a max node, so we will add B1, B2 and B3 to our priority queue. Okay, so we will remove this. We will add B1, which is a min node, which is live, and again infinity and blank. And similarly, we'll also add B2 and B3. Okay, so this is what our queue looks like. Next, what will happen is we will pop the element at the top, okay, which is B1. And once B1 is popped, what do you think will be added? C1. Yeah, that's right. So C1 will be added. So let's pop B1, and in place of that we will add C1, which is a max node, a live node, and again infinity and blank. Okay, so now we will pop C1. Okay, and in place of C1 we will add the two children, which are D1 and D2. Okay, so this will now become D1 and D2. Okay, now what will happen is we will pop D1 next, and in place of D1 we will add E1, right? E1 is the max node with the value 64. Now this is when our algorithm will start to change a bit, in the sense that the priority queue will have some dynamic changes over here. So you added E1, a max node, as of now a live node, okay, with bound infinity, but a value of 64. So when it returns a value of 64, what will happen is we will label this as a solved node, and we will push it to the back of the queue. Okay, because it has now been labeled as solved, it is now being labeled as solved, and it has a value of 64, which is lesser than infinity, right? So it will be pushed to the bottom of the priority queue, and this bound will also change to 64. Okay, okay, one question: will it go to C3 C5 before D1 D2? um, no, it won't go to C3 C5 before D1 D2, because it starts solving one subtree and then goes to the next subtree, right? So when you pop C1, it will first solve the immediately following subtree, which is D1 and D2, right? And once this whole B1 subtree has been solved, then it will go on and look at the B2 and B3 subtrees, where C4 and C3 and C5 are C4 and C5 and C6 are going to figure in. Okay. Okay, so here we don't have any alpha and beta. Okay, so don't confuse this with the alpha beta method. So this is a completely different algorithm, the SSS star algorithm. So here we don't have any alpha beta business. Okay, so we just have the priority queue over here that will help us achieve our solution. Okay, so now we have labeled E1 as solved, and once we label E1 as solved, what will happen is we will add um, the next particular thing that was there. Okay, yeah, sorry about that, I got a bit distracted. So in the priority queue we had D2, right? So now we will pop D2, and when we pop D2, E3 will be added, right? Because D2 has, the first child of D2 is E3 with the value 69. Okay, so E3, which is a max node, which is live, which has bound infinity and a value of 69. So again, E3 is a horizon node, so we will solve it. Okay, we will label it solved, and we will move it to the bottom of the queue. Okay, so will 69, this E3 be placed before or after E1? What do you think? After, are you sure? So think about it in terms of the value. Okay, so E3 has value 69, E1 has value 64, and the others have value infinity. Yeah, it is a queue, but it's a priority queue. Okay, so the elements are entered based on the priority. Yeah, so it will be entered before E1. Okay, so this is where E3 will take place. It will have bound 69, value 69, and its label will be salt. Okay, so yeah, this is where we are at this point of time. Now we will try to pop B2. When B2 is popped, okay, so now we are done with this particular subtree. Okay, we will now pop B2 and we will enter C3. Okay, so we pop B2, C3, which is a max node, live node, infinity bound, and space. Okay, so now we will pop C3, and in place of C3 we will add D5 and D6, which are min nodes. Okay, now D5 will be popped next, and when D5 is popped, E9 will enter, right? So we will have E9, which is a max node, live node, inf, and value 17. Okay, and again this is a leaf node, so again it will be popped and it will be placed at the bottom. Okay, okay, now that we have E9, now we will pop D6, and when we pop D6, E11 will be added. Okay, so let me write it down. E11, max node, live node, and a value of, what is the value of E11? It is 13. Okay, again a leaf node, so again it will get labeled as salt, and it will get added to the bottom. Okay, so clear up till this? Okay, great. So similarly, we are going to proceed with B3 as well. And when we do the whole process with B3, what will happen is E17 and E19 will get added. Okay, so I'm not writing down the whole thing again, the whole steps, but you can understand that E17 and E19 will be uh, added to the priority queue. Okay, so this has value 62 and 31. Okay, so these will get added in the middle. Okay, so now if you notice, we have 6 nodes in our priority queue, and these are the 6 initial clusters that we talked about, right? So this is how the SSS star algorithm arrives at its initial clusters. Okay, does that give some clarity? Okay, that's great. So now that we have the initial clusters, what we will do is we will pop the element at the top of the queue, which is E3. And when E3 is popped, its immediate next neighbor, which is E4, okay, that will now, let me just verify it with the trace that we have. Yeah, so E4 will now get added to the priority queue, but the bound will now change. Okay, so E3 will be popped and E4 will get added with the status live. Bound will be 69, but value will be 68. Okay, so again we'll proceed to solve E4. Okay, we'll label E4 as solved with value 68. Okay, and this will get added over here, I think. No, it'll be added at the top itself. Right. Okay, so this is what our priority queue will look like. Now that both E4 is been given has returned a value and E3 we already knew was solved and just popped out. So we will now say that this D2 has been solved and it will be assigned a value of uh, 68 now. Okay. So E4 got added because that is how the SSS star algorithm is designed. Okay, so once you have got your initial clusters, you'll start with the first element or the top element of your priority queue. You will pop it out and you will add the immediate next neighbor or the brother or sister of that node that you can say. Okay, and once we have E4, we see that it doesn't have any other brother or sister, right? So we will say that the parent of that node has now been solved and we will assign it a value of 68. Okay, so we will say that this is now a value of 68. Okay, and another peculiarity about the SSS star method is that whenever a min node gets solved, okay, we can immediately say that the its parent is also solved. Okay, so once this min node is solved, the 68, we can immediately say that its parent, which is C1, is also solved with value 68. Okay, so now that this is solved, and what we are going to do now is, okay, we are now going to proceed in a similar manner for the rest of the tree. Okay, so I'm not writing down the priority queue again, I'm just referring to the trace that we have over here. So if you recall, I'll just go to the instant where till the point where our solution was. Okay, yeah, so we were at this point, right? So E4 was at the top of the queue with labeled as solved, and E1, E17, E19, E9 and E11 were following it. Now once E4 has been marked solved, its parent, which was D2, is also marked solved. Okay, and once D2 is solved, we pop out D2 and then we add the parent of the, since this is the min node that has been solved, we immediately say that C1 which was the max parent, has now been solved. Okay, and we add that to our queue, and we also prune out E1. Okay, because we know that uh, okay, now that we know that this has been solved with value 68, there is no point looking into this subtree, right? So any element that belong to this subtree will be removed from our priority queue. So E1 will get removed from the priority queue, E4 was already removed, and C1 will now get added. Okay, so this is what our queue would look like. Okay. This is what our queue would look like. Okay. So now when C1 has been added as solved, we will proceed similarly to what we just did. Okay. So we see that C1 has a neighbor, has a brother node, which is C2. So we will now add C2 to our priority queue and proceed to solve it in a similar manner. Okay. What that basically means is that we have solved this, we have added this to our priority queue. Now we will apply the SSS star algorithm recursively to this subtree, and we will get a particular value for this node, which will actually happen to be 68. And you can solve it on your own, or you can look at the trace, and then we'll label this as solved again with value 68. And again, this is a min node that has been solved, right? So immediately when this min node has been solved, we can say that its parent is also solved, and this happens to be a root node. And this also means that there is no point looking into the other subtrees. So this whole subtree will itself get pruned. Okay, this whole subtree will get pruned. So you see that while alpha beta algorithm was doing some pruning, SSS star algorithm goes one step ahead and does a whole lot more pruning. Okay, and I'll show you the final subtree. This is what the final subtree would eventually look like. And we have obtained a value of 68 using the SSS star method. Once again, I'll highly recommend that you go and have a look at the trace yourself, okay, and arrive at the final solution. It looks long, but it's actually very simple. So once you go through it, you won't find much of an issue. Okay. So since we're also nearing the time of our session, I will quickly go through the solution, the question answers, which are actually just based on the SSS star method that we just saw. Okay, so the initial number of clusters was 6, and the initial nodes in the horizon nodes that were in the initial clusters were 1, 3, 9, 11, 17, and 19, as we just saw. Okay. Now, which of the horizon nodes are assigned a solved status by SSS star? Okay. So again, if you follow through the trace, you will, and you keep an account of all the nodes that were assigned a solved status, you will see that those happen to be all the initial clusters that we started with. Okay, so that means E1, E3, E7, E11, E17, and E19, or whatever those numbers were, as well as all the intermediate nodes that got solved while you were going through the process. Okay, so that actually happens to be E1, E3, that belong to the initial cluster, E4, the E4, E5, E6, E9, E6, E9 and 11 were already part of the initial cluster, and E17 and E19 were also part of the initial cluster. So these are all the horizon nodes that were assigned a solved status by the SSS star method. Okay, once again you can verify it using the trace, and that brings us to an end of the questions for today. Sure. So whenever we encounter a horizon node, it already will have a value, right? So it will return that value, and we will mark it as solved and add it to the priority queue in its appropriate place. Now, when we are at a point where there is some neighbor of, when we have arrived at our initial clusters, and we pop an element and we see that this element also has a neighbor, which is a brother or a sister node, Okay, now we add that to the priority queue, and we keep doing that until we have neighbors or brothers or sisters of that node left. Once we don't have any brothers or sister nodes left, we can say that the parent node of that particular element is labeled solved. Okay, and once that solved node is a min node, we immediately say that the max parent of that min node is also solved, and accordingly we prune the subtrees that are no longer useful to us. Okay, so I hope that addresses your question, Abhishek. um, yeah, so so we covered most of the methods with some example or the other. I will upload the Jamboard slides as well. The traces and the question answers have already been uploaded in the folder, and the videos will be uploaded by tomorrow. Okay, so yeah, if in that case, we can now close this session, and we'll meet next week. Thank you all for attending, and let's meet next week.
Thank you, sir. Thank you very much.